Good afternoon. This file contains the pre-lecture notes for lecture on Thursday, October 17th, 2013. The relevant reading for this pre-lecture can be found at the end of Chapter 8 in the Carey textbook, sections 8.7 through 8.12. For this pre-lecture, we continued the discussion we began on Tuesday with regard to the different factors that affect substitution reactions. Specifically, we'll talk about SN1 mechanisms in this pre-lecture. On Tuesday, we had discussed the factors that affect SN2 mechanisms. We'll also return to elimination reactions, which we talked about several weeks ago, in order to differentiate between substitution and elimination as competing processes in the same reaction. So first, let's begin by reviewing the characteristics of the SN1 mechanism. Recall that the SN1 mechanism displays first-order kinetics, which means that the rate-determining step of this mechanism is unimolecular. Only the concentration of the alcohol or alkyl halide matters in the rate-determining step for SN1 reactions. Because we have a unimolecular rate-determining step, we form a carbocation intermediate. The rate then is determined by the relative stability of that carbocation intermediate, and because it's a carbocation, it of course can rearrange. The stereospecificity of the reaction is nonspecific, which means that when we begin with any chiral compounds, we will always create optically inactive racemic mixtures in our products due to the fact that the carbocation intermediate is planar, which means that it can be attacked by a nucleophile from either side. Here on these few slides, I've drawn out the mechanism using our curved arrow approach. Again, this mechanism is SN1, not SN2, because the rate-determining step involves the leaving group leaving to form the carbocation. This is our highest energy step in the reaction, which makes it unimolecular. In the second step of the reaction, here a salicylic reaction, the nucleophile, we're using water in this case, comes in to attack the carbocation intermediate to form an oxonium ion on our way to our final product. Of course, as we've seen many times over, deprotonation is required to produce the final alcohol from this SN1 salicylic reaction. Again, let me emphasize, SN1 mechanisms produce racemic mixtures. They are not stereospecific due to the planar shape of the carbocation intermediate. Here from your textbook, we can see some 3D images that help us understand the planarity of the carbocation intermediate. As we've seen before, the rate-determining step of the SN1 mechanism involves the leaving group leaving. Here we have our carbocation intermediate. Note that it's planar with an empty p orbital orthogonal to the plane that includes all of the sigma bonds to the carbocation. This planar carbocation intermediate can be attacked from either side, either lobe of the p orbital, to produce a 50-50% racemic mixture of two enantiomers. In any case where the leaving group shields the front side of the carbocation such that it cannot get away, we would get a more than 50% inversion at the stereocenter. We'd be able to determine this by the solvent structure, which we'll talk about a little later in the pre-lecture. So here, using dash wedge perspective formulas, we can also see how the stereochemistry of an SN1 reaction produces racemic mixtures. If we begin with R minus 2-bromooctane, to produce 2-octanol, we get both a combination of S plus 2-octanol and R minus 2-octanol. We don't get only one of the stereoisomers due to the fact, once again, that the nucleophile, in this case the solvent water, is able to approach the carbocation from either side after the leaving group leaves. Don't forget, as always, when we have carbocations, you can have rearrangements. Always check to see whether you can increase the stability of the carbocation by doing a hydride or an alkyl shift to create a tertiary carbocation before you do your subsequent attack by the nucleophile. Let's now talk about the different factors affecting the rate of an SN1 reaction. Unlike the SN2 reaction, we only have two factors that we have to consider. For SN2 reactions, we had four factors to consider, so this is a little bit simpler to get a grasp on. Those two factors include the stability of the carbocation. This is the same thing that you've already talked about in terms of the E1 mechanism, as well as the solvent structure. So first, let's talk about that stability of the carbocation again. This is known, of course, as a stereoelectronic effect. The rate of all SN1 reactions are governed by this stereoelectronic effect. Because the carbocation formation is the rate determining step, any factors that contribute to the stability of that carbocation will increase the rate of an SN1 reaction. So, you should be able to predict the relative rates that you see in Table 8.5 from your textbook. In SN1 reactions, we increase the rate of reaction by increasing the number of alkyl substituents around the alpha carbon. So, methyl bromide reacts slower than ethyl, which reacts slower than isopropyl, which reacts slower than terbutyl bromide. This is because the formation of the carbocation increases in the number of substituents as we go down the table, from a primary to a secondary to a tertiary carbocation. Tertiary carbocations are so stable, in fact, that the relative rate of an SN1 reaction with a tertiary alkyl halide is many orders of magnitude faster than with a secondary, primary, or methyl carbocation. Here's an example of another solvolysis reaction. Note a rearrangement has occurred in this reaction. The first step, of course, would be the leaving group leaving the bromide, leaving the blue alpha carbon to generate a secondary carbocation. Note again that that secondary carbocation is right next door to a tertiary hydrogen. It's vicinal to a tertiary hydrogen, which means we can have a hydride shift in order to increase the stability of the carbocation. This hydride shift creates a much more stable carbocation, which means this pathway to create the tertiary alcohol occurs much faster than this pathway here, which would produce a secondary alcohol. Thus, we get the tertiary alcohol as the major product of this SN1 reaction. Second factor that you have to consider is the solvent structure for the rate of an SN1 reaction. Unlike SN2 reactions, SN1 reactions preferentially occur in polar protic solvents. This is because a polar protic solvent can stabilize the carbocation. Remember that in polar protic solvents you have acidic protons available, which can contribute to hydrogen bonding in the solvent. The availability of lone pairs on any heteroatoms in the solvent can then coordinate with the carbocation in a hydrogen bonding network to stabilize the carbocation through an electronic effect. Therefore, any cases in which you place an SN1 reaction in a polar protic solvent will occur much faster than cases in which you place an SN1 reaction in a polar aprotic solvent. Don't forget that the opposite is true for an SN2 reaction. Those occur faster in polar aprotic solvents, not polar protic solvents. Here we can see from the table in your textbook the relative rates of different solvents that can be used for SN1 solvolysis reactions. We're looking at acetic acid, methanol, formic acid, and water. Note that as you go down the table, the dielectric constant increases. That means the polarity of each of the solvent particles is increasing, and we can see that the rate increases linearly as we increase the dielectric constant of our solvent. So the more polar a solvent is, the faster an SN1 reaction will occur. So let's do a quick recap of the mechanisms for SN1 and SN2 to summarize how we would determine the difference between the two mechanisms if we were trying to decide will a reaction occur via an SN1 pathway or an SN2 pathway. So, in any case where you have a primary alkyl halide undergoing nucleophilic substitution, it will always react via the SN2 mechanism. This is due to the fact that the formation of an formation of a carbocation via an SN1 mechanism would be unfavorable due to the instability of the carbocation. So primary alkyl halides are going to react via an SN2 mechanism. In contrast, tertiary alkyl halides will undergo nucleophilic substitution via an SN1 mechanism. Remember, tertiary alkyl halides will produce tertiary carbocations, which are very stable for SN1 mechanistic pathways. In contrast, SN2 is not favored for tertiary alkyl halides because of the crowding around the alpha carbon prevents the approach of the nucleophile. In some sense, we need to get the leaving group to leave first at a tertiary alpha carbon so that the nucleophile can approach. This happens only via an SN1 mechanism. So the big question you should be asking is what happens with a secondary alkyl halide? Turns out these can undergo either SN1 or SN2 mechanisms. In cases where we have a poor nucleophile, a weak nucleophile, like a solvent particle, SN1 mechanisms will be favored. In cases where you have good nucleophiles, like anionic nucleophiles, SN2 mechanisms will be favored. So, three factors to consider here in determining whether you'll have SN2 or SN1 mechanisms. How much crowding is around the alpha carbon? What is the solvent that the reaction is taking place in? And what is the nature of the nucleophile that you're working with? These factors will help you determine whether an alkyl halide is undergoing SN1 or SN2 mechanisms. Now, prior to covering substitution mechanisms, we discussed elimination mechanisms towards the beginning of the quarter. I've said in a couple of instances that substitution and elimination are competing reactions. In any case where you have an alkyl halide combined together with the nucleophile, two possible types of products can occur. You can either eliminate the beta hydrogen and the leaving group to produce an alkene, or you can substitute the leaving group with the nucleophile to do a substitution reaction. We'll conclude this pre-lecture by discussing all of the different factors that favor substitution versus elimination so you can determine which of the two functional groups will be the majority product in a competing elimination and substitution reaction. So, we begin first by using a systematic approach where we set sort of a starting line and all agree that a typical alkyl halide, such as a secondary alkyl halide, combined with a typical Lewis base, an alkoxide, a strong nucleophile, a strong base in this case, this combination of a secondary alkyl halide with a typical Lewis base will favor elimination by the E2 mechanism. We set this as our starting point, and then we compare if we manipulate any of the factors that we know favor elimination or substitution, how can we push the direction of the reaction one way or the other. But begin first by agreeing that the major reaction for a secondary alkyl halide with an alkoxide ion will be elimination via E2. So here's an example of this. On this slide I have isopropyl bromide. Note that it's a secondary alkyl halide. I'm combining it together with a strong base, an alkoxide anion in ethanol. The major product of this reaction is the elimination product, the alkene, not the substitution product. Note that the substitution product occurs as the minor product. Both are possible, but the major product is the alkene due to the fact that we're working with a secondary alkyl halide and a strong base. We can favor substitution in the system in any case in which we decrease crowding at the carbon with the leaving group on it. Remember, substitution needs to occur via either SN2 or SN1 mechanisms. In any case where the nucleophile can approach from the backside of the alpha carbon easily, substitution via SN2 will occur. So by decreasing the crowding at the alpha carbon bearing the leaving group, we'll favor an SN2 mechanism. This occurs in any case where you have a primary alkyl halide. A primary alkyl halide, note in this case we have propyl bromide reacting together with the same nucleophile, a strong base, produces the ether product, the substitution product, as the major product compared to the elimination product. This is because the primary alkyl halide has less crowding around the alpha carbon. Secondary alkyl halides with strong bases favor elimination. Primary alkyl halides with strong bases favor substitution. We can manipulate primary alkyl halides to create alkenes by manipulating the base. Remember, we want to decrease the number or decrease the amount of crowding around the alpha carbon to favor substitution. So if you have a primary alkyl halide, if you use a very large bulky base, the nucleophile still can't get in even though the alpha carbon has little crowding. It's the base in this case that has lots of crowding around it, which prevents approach of the nucleophile. So in this case, you can force a primary alkyl halide to undergo elimination if you use a bulky base like terp-butoxide, our go-to base for elimination reactions. We can also increase the substitution as our mechanistic pathway by decreasing the basicity of the nucleophile. Weak bases, recall from Tuesday's lecture, are more likely to undergo substitution reactions than elimination reactions. So, if we take secondary alkyl halides and combine them together with weakly basic nucleophiles, we will get substitution instead of elimination. Note here the pKa of hydrogen cyanide. This is a somewhat strong acid, which means that its conjugate base, cyanide anion, is fairly weak as a base. It's still a good nucleophile, but it's a weak base. As such, we get, instead of elimination, substitution of chloride by cyanide. In any case, though, where we use a secondary alkyl halide plus a strongly basic nucleophile, don't forget that the major product of this reaction will be an elimination. Once again, secondary alkyl-halides plus strongly basic nucleophiles always eliminate as their major product. If you replace this strongly basic nucleophile with a weakly basic nucleophile, you can instead get substitution at the alpha carbon. We've talked about secondary alkyl halides and primary alkyl halides. All that's left is tertiary alkyl halides. Tertiary alkyl halides have so much crowding around their alpha carbons that they will always favor elimination under second order kinetics. It is only in cases where you're working with solvolysis under first order kinetics can you get substitution to predominate over elimination. Let's look at an example of this. Here I have a tertiary alkyl bromide combined together with a strong base sodium ethoxide in a solvent ethanol. The major product of this reaction, as predicted, are the alkene products, the elimination products. In fact, these two alkene regioisomers, or constitutional isomers, comprise 99% of the products produced from this reaction. We only get 1% of the products being the substitution reaction. Elimination is favored, again, when you have tertiary alkyl bromides with strong bases. Replacing the sodium ethoxide solely with ethanol, though, we can promote a solvolysis reaction in which now we favor substitution over elimination. The reason for this, of course, is because the leaving group leaves in the first step of this solvolysis reaction to produce a tertiary carbocation, which can easily be substituted from either side by the ethanol solvent particles. Okay. Elimination, in contrast, requires the breaking and formation of two bonds, whereas the solvolysis reaction for substitution requires the formation of only one bond, so substitution is favored under conditions where alkyl halides are combined together solely with solvents. The last slide in the pre-lecture includes a table for you considering all of the factors side by side that will help you determine whether a reaction is substitution or elimination and whether the mechanism is first order or second order in its kinetics. Remember, you must consider the solvent that the reaction takes place in, the substitution pattern around the alpha carbon, whether it's tertiary, secondary, or primary, the nucleophile that you're working with in terms of whether it's a weak nucleophile or a strong nucleophile or a strong or weak base. The leaving group is the same in all cases, so the rate can be increased for all of them when working with good leaving groups. The differences between the steps in each of the pathway. Note that all unimolecular processes are multi-step, while all bimolecular processes are concerted. On the last two columns here, I've just indicated for you some features of each of these mechanisms. These last two columns don't help you determine whether it's substitution or elimination, but they do help you determine what the stereochemistry or the regiochemistry will be of each reaction once you make a determination whether it's substitution or elimination based on the solvent, the starting material, and the nucleophile. So, with that, this pre-lecture is concluded. As always, make sure to read those relevant sections in your Carey textbook and come to class prepared to apply what you have learned.